Application of NRAP Tools to the futuregen 2.0 site by Diana Bacon, Pacific Northwest National Laboratory. As part of NRAP's Task 5, we revisited characterization data and modeling from the UIC Class 6 permit application for the futuregen 2.0 site. We've used this as a test case to apply NRAP tools to determine risk-based area review, monitoring design, post-injection site care period, and containment assurance and accounting. We have several publications applying the SOSAT, NRAP OpenIAM, and DREAM tools to this site. I'll be discussing these last three, two of which were published recently and one that has been recently submitted. The futuregen 2.0 CO2 storage system consisted of 4 horizontal injection wells injecting into the Mount Simon sandstone at a depth of approximately 4,000 feet. The primary confining zone was the Eau Claire Formation, and a secondary confining zone was the Davis member of the Franconia Dolomite. A total of 22 million metric tons was planned to be injected over 20 years, 1.1 million metric tons of CO2 per year. The dataset consists of subsurface characterization data, both regional and measurements, as well as a reservoir model and a leakage model that we were able to use to construct component models for NRAP OpenIAM. Subsurface characterization data includes seismic, borehole VSP, geophysical logging, core analyses, gravity and geodetic surveys, in situ stress characterization, and hydrologic field tests. A stratigraphic borehole was drilled and was used to develop the initial reservoir models. Borehole data from the stratigraphic well and from regional boreholes and published regional contour maps were used as input data to develop the geologic model for the site. The reservoir numerical model covers a 100-mile square lateral domain, and it includes the injection zone from the Mount Simon up through the secondary confining zone, the Davis, Ironton, and Franconia. It has a boundary-fitted grid representing the dipping strata and 51 hydrostratigraphic layers, with homogeneous properties within each layer. We used a simpler 31-layer model for our analyses. The leakage model was developed to investigate the potential for water quality impacts associated with loss of supercritical CO2 or brine from the storage operation as part of the Class 6 permit application. The model domain extends vertically from the first permeable unit above the primary confining zone to the limestone units just above the lowermost USDW. The stratigraphy and rock properties from this model were used as the basis for the futuregen 2.0 aquifer component. This shows a workflow for performing risk-based area of review and monitoring design using NRAP OpenIAM and DREAM. To begin with, reservoir simulations of carbon storage are used to develop reservoir lookup table components for NRAP OpenIAM. Then, NRAP OpenIAM is applied twice. First, using the open wellbore component and an aquifer impact component to determine a risk-based area review. Then, after identifying legacy wells within the area of review, NRAP OpenIAM is applied again using the multi-segmented or cemented wellbore component to generate more conservative leakage scenarios to be used as input to DREAM for monitoring design. The area of review for a carbon storage site is the area surrounding the injection project where groundwater resources may be endangered. The EPA requires operators applying for a Class 6 CO2 injection permit to determine the area of review based on the separate phase CO2 plume pressure evolution predictions from physics-based computational modeling. The area of review is delineated by the maximum extent of the CO2 plume and pressure front over the lifetime of the project to account for risks associated with both CO2 and/or brine leakage into the overlying groundwater aquifer. So the pressure front under pressurized or hydrostatic conditions is delineated by the critical pressure that can cause fluid flow from the injection zone into the groundwater aquifer through a hypothetical open conduit. Under hydrostatic conditions, the critical pressure is the pressure increase that can cause displacement of the existing fluid in the borehole. Under underpressurized conditions, a simple mass balance calculation can be used that assumes the density of the fluid in the wellbore is uniform and equal to the density in the injection zone. But in conditions where the reservoir is overpressurized with respect to the USDW, the determination of an allowable pressure increase is more complicated. EPA guidance states that this allowable pressure increase should prevent fluid leakage into the aquifer and impact on groundwater quality. It can be calculated based on a multi-phase numerical model designed to model leakage through wellbores and a numerical or analytical approach to determine the threshold above which an impact to an aquifer occurs. So we propose to place hypothetical open boreholes across the site and determine whether an aquifer impact would occur or not at each location. At the futuregen site, the reservoir is overpressured with respect to the lowermost USDW. So even if no CO2 were injected, brine could still flow from the reservoir to the USDW through an open conduit. The EPA specified that limiting the pressure increase in the aquifer to 10 psi would be protective of the aquifer. Based on reservoir simulation, this resulted in an area of review 65 kilometers in diameter. This is the workflow for calculating a risk-based area of review using NRAP OpenIAM. First, run the integrated assessment model, varying reservoir, wellbore, and aquifer properties stochastically. For each XY location in each model realization, calculate the maximum pH and TDS impact volumes over all simulation times. Finally, as shown in the figure, for each XY location, calculate the percentage of non-zero aquifer impact volumes for all model realizations. The figure shows that close to the injection well, the TDS aquifer impact probability is 100%, decreasing with radial distance from the well. The boundary with 0% aquifer impact probability coincides with the 0.1 megapascals contour for maximum pressure increase in the reservoir. Determining no net degradation or no impact threshold values is the preferred approach for establishing minimum thresholds for aquifer impacts due to leaking fluids from carbon storage reservoirs. This approach takes into account the temporal and spatial variability in monitoring metrics in order to statistically determine reasonable thresholds beyond which degradation of aquifer quality has occurred. However, not all sites have sufficient baseline measurements to calculate no net degradation threshold values. Because no information was available on spatial or temporal variability in pH or TDS for the St. Peter sandstone, the precision of pH and TDS sensors were used to set these thresholds when developing the futuregen 2.0 aquifer component. The risk-based area of review has a diameter of 38 kilometers compared to the original area of review, which had a diameter of 65 kilometers. The risk-based area of review can still be considered a conservative estimate due to the low aquifer impact thresholds selected. The next step in transition to the monitoring design workflow is to identify potential leakage paths within the area of review. No legacy wells were identified within the area of review, so the only potential leakage paths are the stratigraphic well and the injection well, shown here in comparison to pressure increases and the CO2 footprint in the reservoir. We considered 4 potential leakage layers: the Ironton sandstone, which was the above confining zone, or ACZ, 2 potential thief zones, the Potosi dolomite and the New Richmond sandstone, and the lowermost USDW, the St. Peter sandstone. Assuming a distribution of wellbore permeability values based on the highest observed values for legacy wells, We use DREAM to analyze in which of these layers the earliest and largest leaks might occur. While the original monitoring plan called for 2 monitoring wells in the above confining zone, DREAM's monitoring plan, optimized for early detection, calls for just 2 monitoring wells in the above confining zone. This results in a $10 million savings for the project. The analysis also shows that potential leaks in the USDW are likely to be relatively small. We also used this analysis to demonstrate determination of a risk-based post-injection site cure period. As a first-of-its-kind project, the US EPA recommended the use of the default 50-year post-injection site cure, or PISC period, for the underground injection control Class 6 permit application. To close a site, the Class 6 regulations require demonstration of non-endangerment. The futuregen 2.0 project did not take credit for projected reservoir performance in determining a PISC period. Based on reservoir simulation, the CO2 plume was projected to stabilize 2 years after injection stopped, and reservoir pressure was projected to decline rapidly after the 20-year injection period. NRAP OpenIAM stochastic realizations indicate that the majority of risk of endangerment to the USDW occurs during the injection period. A 10-year PISC period would still lead to a net PISC period reduction of 40 years and an operational cost reduction in excess of $50 million for the project. Our last application of NRAP OpenIAM at the futuregen 2.0 site relates to containment effectiveness. Geologic carbon storage practitioners can claim tax credit under 45Q based on a justification that CO2 has been stored securely. How can NRAP OpenIAM be used to forecast containment effectiveness and inform decisions about taking credit for storage? The workflow for determining containment effectiveness at the futuregen 2.0 site involved utilizing the previously developed system model to run 10,000 stochastic simulations of storage performance. Next, the containment envelope and thresholds for containment effectiveness were defined. The ensemble of simulation results was then used to inform the probability distributions in a Bayesian or decision network. Finally, the Bayesian network was used to infer whole site containment assurance given monitoring observations and mitigation decisions. 2 containment envelopes were defined. The smaller containment envelope included the injection zone and the above confining zone interval, the Ironton-Galesville. The larger containment envelope includes the 2 overlying thief zones, the Potosi Dolomite and the New Richmond Sandstone. The stochastic simulation results were used to construct empirical cumulative density functions for the CO2 mass leaked 70 years after the start of injection. For all the scenarios evaluated, the probability of containment is close to 1 if the larger containment envelope and the lower 99.9% storage criterion are chosen. In general, the probability of containment increases with the size of the containment envelope and inversely with the storage criterion. Based on the results of the stochastic simulations, the mass of CO2 leaked was divided into 5 classes to simplify construction of the decision network. Also, monitoring thresholds were divided into 2 classes for each aquifer because the seismic detection thresholds increase with depth. The Bayesian network for the smaller containment envelope has 6 nodes. The 3 nodes on the left denote CO2 leakage mass into the above confining zone, referred to as aquifer 1. Over time, CO2 leakage mass out of the containment envelope over time, less than 70 years, and CO2 leakage mass out of the containment envelope after 70 years. The 3 nodes on the right of the graph denote surface seismic monitoring implemented at the site, mitigation activity, and cumulative CO2 leakage mass out of the containment envelope after 70 years if mitigation is performed. These graphs show how the probability of containment is affected for 3 different storage criteria, assuming either a low or high threshold monitoring detection, and mitigation decision. In general, the probability of containment increases if leakage either is not detected or is detected and mitigated. This chart shows the effect of updating the network for 3 different storage criteria, using additional information from monitoring for the large containment envelope and a low detection threshold monitoring observation. The estimated probability of containment can be further increased if the monitoring method can not only detect the CO2 plume, but also provide information about the depth interval and the mass of the CO2 plume. So in conclusion, the application of NRAP OpenIM and DREAM to the futuregen 2.0 site showed that a risk-based area of review can be calculated using NRAP OpenIM based on potential aquifer impacts. Risk-based monitoring design using DREAM resulted in a simpler monitoring network design. NRAP OpenIM can define a risk-based and substantially shorter PISC period for the site, and can also inform construction of conditional probability tables for a Bayesian network to infer containment performance from monitoring observations and mitigation decisions. Thanks for listening. Here are some additional references that I mentioned during the talk.